Let's see where we are now with building the solution to the model checking problem. For any formula psi, we constructed the automaton auth psi. And then for any LTS m, state S0 and formula phi, we constructed the product automaton m S0 times auth not phi. It is easy to see that these are computable steps, in that the constructions can be performed in any Turing-complete programming language. You can write a program that takes m as 0 and phi as an input and returns the above product automaton. And our overall correctness theorem reduces the model checking problem, which is about determining whether m in state S0 satisfies phi, to the problem of determining whether the language accepted by the product automaton is empty. Next, we're going to show that this last problem, emptiness for this particular kind of automata, generalized non-deterministic Buki automata, GNBA for short, is algorithmically decidable, which in particular will show that the LTL model checking problem is also algorithmically decidable, thanks to the computational reduction of the latter problem to the former problem. Just to be sure, by the decidability of the emptiness problem for GNBAs, sometimes I call it algorithmic decidability, sometimes just decidability, with is the same thing. I mean that there exists an algorithm, think a program written in your favorite programming language, that takes as input a GNBA auth, always terminates, and returns the answer yes if the language accepted by auth is empty, and no if the language accepted by auth is non-empty. To prove this theorem, we first need a lemma, which will talk about the underlying graph of an automaton auth. The graph of auth, denoted like this, has the automaton states as nodes, and its edges are given by the automaton's transition relation by ignoring the labels. We'll also write arrow to denote edges in this graph. So Q1 arrow Q2 will mean that there exists an edge in this graph between Q1 and Q2. In short, the graph is obtained from the automaton by forgetting the labels on the transitions. In preparation for the lemma, let me now recall some graph concepts. Let G be a directed graph with nodes at Q and edges denoted using arrow. Note that we allow self-edges, edges between a node and itself. All concepts on this slide will be relative to the graph G. You should all be familiar with what a finite path in a graph is. It is a finite sequence of nodes consecutively connected by edges. And the node Q prime is said to be accessible from a node Q if there is a path from Q to Q prime. For example, if Q1, Q2 up to Qn is a path, then Qn is accessible from Q1, and also Qj is accessible from Qi if I is smaller than j. A cycle is a path that contains at least two nodes and has its first and last nodes identical. It can include other repetitions besides the first and last node. Note that in a cycle, every node is accessible from every other node, and also from itself. A lasso is a path ending in a cycle. So if we can draw a cycle like this, a lasso would look like this. So it starts here. It has a stem, so it goes this way. And then it gets into a cycle. So it has a stem part and a cycle part. There's a stem followed by a cycle. A strongly connected component is a set C of nodes such that any two nodes in it are connected by a path that goes through nodes in C only. Another way to say this is that every node in C is accessible from every other node in C using only nodes in C. Strongly connected component is going to be abbreviated SCC. Note that the nodes of any cycle are a connected component, form a connected component. And conversely, the nodes of any connected component can be organized as a cycle, possibly involving repetitions of nodes. Remember that in our cycles, we allow repetitions. So it can look like this, but can also look like this, or like this. A strongly connected component will be called maximal if there is no other strongly connected component that strictly includes it, in that it contains all its nodes and at least one more node. A strongly connected component is called non-trivial if it has at least one edge between its nodes. Note that any connected component with at least two nodes is necessarily any strongly connected component with at least two nodes is necessarily non-trivial. And also, a single node strongly connected component is non-trivial if that node has a self-edge. Let's illustrate these concepts on a concrete example, the graph shown here. You can follow on the picture to see that Q1, Q1, this node with a self-edge, forms a cycle. And also Q1, Q2, Q1 forms a cycle. And Q2, Q3, Q1, Q2. These are all cycles. And here are some examples of lassos where I draw the stem in brown and the cycle in blue. So we have, for example, this one is a lasso that starts with Q0, moves into Q1, then to Q2, where it starts forming a cycle, namely Q3, Q1, Q2. And here are some examples of strongly connected components. The singleton Q0 forms a strongly connected component that is maximal, since there's no strongly connected component that includes it strictly, and is also trivial, since there's no edge between its nodes. On the other hand, the singleton Q1 forms a strongly connected component that is not maximal. For example, Q1, Q2 is a strongly connected component that includes it strictly. And also Q1 is non-trivial, since Q1 has a self-edge. Q1, Q2 is also a strongly connected component that is not maximal and non-trivial. It is non-maximal because, for example, Q1, Q2, Q3 is a strongly connected component that includes it strictly. Finally, Q1, Q2, Q3 is a strongly connected component that is both maximal and non-trivial. This is the kind of strongly connected components we'll be interested in. Why is Q1, Q2, Q3 a strongly connected component, by the way? Simply because any two of its nodes are connected by paths. And the same applies to all our examples of strongly connected components. You can easily check that they are so. Note that any directed graph can be partitioned into disjoint maximal strongly connected components, trivial or not. Here we have two of these, a trivial one, Q0, and a non-trivial one, Q1, Q2, Q3. Back to our automaton OT. An accepting lasso for OT will be a lasso in its underlying graph that has two properties. First, it starts in an initial state of the automaton, and second, it has a non-empty intersection with all the accepting sets of the automaton. More formally, it is a path of this form where Q0 is in I, Qn plus 1 is the same as Qm. So sorry, Qm plus 1 is the same as Qm plus n. So this is the cycle part of the lasso. And this cycle part contains elements from all the accepting sets F in graphic F. For example, let's take the automaton shown in the picture, where Q0 is the only initial state, and there are two accepting sets, Q0, Q1, and Q0, Q2. Then Q0, Q1, Q2, Q1 is an accepting lasso. So it starts here, and it then goes to Q1, starts the cycle here in Q1, Q2, Q1. So Q1, Q2 form the cycle of the lasso. Why is it an accepting lasso? Because its cycle part contains Q1, so it intersects the accepting set Q0, Q1, and also contains Q2, so it intersects the accepting set Q0, Q2. So its cycle part intersects all the accepting sets. And of course, it starts in the initial state Q0. And similarly, this one, Q0, Q1, Q2, Q3, Q1, is an accepting lasso for essentially the same reasons, as you can check on the picture. On the other hand, this one, Q0, Q1, Q3, Q1, is not an accepting lasso. So it looks like this. Start with a stem, Q0, Q1, and then we have the cycle Q1, Q3. We have the cycle between Q1 and Q3. Why is this not an accepting lasso? Because it does not intersect one of the accepting sets, namely Q0, Q2. Okay, so an accepting lasso starts in an initial state and visits all the accepting sets. It does not need to visit all the elements of an accepting set, but should visit at least one element from each accepting set. Note that the concept of an accepting lasso only uses from the automaton the underlying graph, the initial states, and the accepting sets of states. So it does not refer at all to the labels on the transitions, which is helpful to note, since we can clean up the picture a little bit when discussing accepting lassos, as I'm doing now with this picture. Now, let's take the lemma that will help us prove decidability. For an automaton auth, non-emptiness of its language is equivalent, on the one hand, to the existence of an accepting lasso, and on the other hand, to the existence of a maximal, non-trivial, strongly connected component of the underlying graph, which is accessible from the initial state and intersects every accepting set. Let's prove the equivalence of the first two statements. First, let's assume that there exists an accepting lasso where Q0, Q1 up to Qm indicate its stem, and Qm plus 1, Qm plus 2 up to Qm plus n indicate its cycle. In particular, Qm plus 1 and Qm plus n are equal. Applying the definitions, we find the word x0, x1 up to xm, then xm plus 1 up to xm plus n minus 1, consisting of letters that label in the automaton the transitions between consecutive states qi in the lasso. So qi, each qi transits through xi to qi plus 1. Because Qm plus 1, Qm plus 2 up to Qm plus n is a cycle, we can iterate it infinitely, and we can also iterate infinitely the corresponding portion of the finite word. This gives us an infinite word, shown here. And a corresponding run for it, shown here. This run, formed of the QIs, is accepting because, by the definition of an accepting lasso, the cycle portion of the lasso intersects all the accepting sets. And it is repeated infinitely, meaning that the run will visit all the accepting sets infinitely often. We conclude that the constructed infinite word is in the automaton's language, so the language is non-empty. For the other direction of this equivalence, assume that the language of the automaton is non-empty, and let x0, x1, and so on be an infinite word accepted by the automaton, and let q0, q1, and so on be an accepting run for it. The set of states is finite, so there exists some state q that appears infinitely often on this run. And let's choose some position I on the run where q appears, so that qi is q. Since the run is accepting, it means that it visits all the accepting states infinitely often. And let's pick a position j further up in the future, greater than I, so that between I and j, all the accepting sets have been visited. In other words, the portion of the run between qi and qj contains states from every accepting set. And remember that q, which is the same as qj, also occurs infinitely often on the run, which means that we can find a k greater than j, such that q appears on position k as well. So I found a portion of the run, namely that between qi and qk, which on the one hand is a cycle, and on the other hand contains an item from every accepting set. This makes the initial portion, q0, q1 up to qk, an accepting lasso, since q0 is also an initial state. And we are done, since we found an accepting lasso. If we are to draw the picture, we have this is q0. Later on, we have qi. Then later on qj in this q sequence. And then qk. And we have the cycle between qi and qk. And from q0 to qi, we have the stem. This is our lasso. Now let's prove the equivalence between the second and third statements. First, let's assume the nodes on the lasso's cycle form a non-trivial strongly connected component, which is included in a maximal non-trivial strongly connected component, C. Indeed, it is to see that non-trivial strongly connected component is included in a maximal. Every strongly connected component, for that matter, is included in a maximal one. If it itself is maximal, done. Not, then there exists another strongly connected component included, and we ask if that one is maximal, and it means there is a larger one, and so on, until we reach a maximum one. This is the argument. Now, the maximal component C contains states for each accepting set, given that already the nodes of the cycle had this property. And, and the stem of the lasso gives a path from an initial state to a state in C, which makes C accessible from some state in I. And we are done. For the other direction of the equivalence, we start with a maximal strongly connected component C that is accessible from an initial state and intersects every accepting set. So we have a path from some initial state Q0 to some state Q1 in C. This will form the stem of our desired accepting lasso. And because C is strongly connected, we can write a cycle that contains all its elements starting with Q1. It is easy to see that the lasso formed with the indicated stem which is Q0 up to the state before Q1 on the path, and the indicated cycle, the one shown here, is an accepting lasso, which concludes the proofs of this direction and concludes the proofs of the lemma. We proved 1 if and only if 2, and then 2 if and only if 3. So all three statements are equivalent. Now, to prove the decidability theorem, we will use the equivalence between 1 and 3 in the lemma. So we want to prove that the emptiness problem for GMBAs is decidable. We must exhibit an algorithm that, given an automaton auth as an input, decides whether the language accepted by auth is empty. According to the lemma, it suffices to decide condition 3, the existence of a maximal non-trivial strongly connected component that is accessible from some initial state and intersects all the accepting sets. And it should be quite clear that this condition is decidable. Starting with a GNBA as an input, and letting G be its underlying graph, we first compute the graph's maximal non-trivial strongly connected components, C1 up to Cm. It is clear that these are computable, and for example, Tarjan's depth-first search algorithm gives an efficient way to compute them. Then, for each component, for each strongly connected component Ci, for each maximal non-trivial strongly connected component Ci, we check that it is reachable from some initial state. Again, a computable step. We start with the initial states and compute their successors, and then the successor of their successors, and so on. And we stop if we found an element of Ci, in which case we conclude that it is accessible, or we have no more states to explore, in which case we conclude that it is not accessible. Also, for Ci, we check if it has elements in common to each of the accepting sets. So this is the second condition that we check, besides reachability. So if we found one of the components, Cj, satisfying this property, we return that the accepted language is not empty. Otherwise, we return the answer, the accepted language is empty. Okay, so essentially after we prove the lemma, 1 if and only if 3, we can see that the problem 1, which we were trying to decide, being reducible to the problem 3, which is quite clearly decidable, gives us a solution to the decidability problem. So in the algorithm that I have shown here, I simply showed the obvious steps that we need in order to decide 3. As homework, please implement this algorithm for deciding emptiness using your favorite programming language, and discuss any design and implementation decisions.